Quantum mechanics is probably the most mind-blowing theory of all of modern physics. In many explanations, cats are simultaneously alive and dead, and the outcome of experiments depends on a person looking at the experiment. Those last two things are kind of sketchy explanations that quantum practitioners have long since abandoned. However, there are a real series of quantum measurements that are just staggeringly bizarre and totally worth talking about. Probably the simplest measurement to understand the weirdness of quantum mechanics is the double slit experiment. And by simplest, I don't mean simple. I mean that it's at least possible to understand how the experimental outcome depends on a relatively few simple knobs in the apparatus. So how does the double slit experiment work? Well, basically, you shine light on two slits, and the light passes through them, and you see what pattern appears on a distant screen. The easiest way to do it is to shine a laser at two parallel slits and see what pattern you see on a distant wall. The laser passes through both slits, and the light going through each slit interferes with one another, and the result is a series of bright and dark lines on the screen. Where the peak of the wave of light going through one slit coincides with the trough of light going through the other slit, the result is a dark spot. If peaks or troughs from both slits line up, then you get a bright spot. You can see similar behavior if you just use water waves. After a wave passes through the slits, there are places in the water where the waves are big and places where there are no waves at all. The first version of this experiment with two slits was performed back in 1801 by British polymath Thomas Young. His work showed that light acts like a wave, and countless physics students reproduce his experiment each year in introductory laboratories. So what happens if there is only one slit, not two? In that case, there's no interference. This stems from the fact that light has only one source. And if you have some physics training, you'll realize that I'm ignoring diffraction here. It just simplifies the discussion, and this whole thing is complicated enough that we need as much simplification as possible. Okay, to recap. With light, we can have one slit or two. If we have one slit, we don't have bands of light on a distant screen. If we have two slits, we do. This pretty much proves that light is a wave. Now let's start talking about tricky stuff. We know from other experiments that light is also a particle, and that particles of light are called photons. That is its own mind-blowing thing because waves and particles seem to be so different, but let's just accept this fact. Proving it would require its own video. So what would we expect if light acted like a particle when it went through the double slits? Well, a particle is like a BB or a marble or something. The particle would go through one slit or the other, but not both. The resulting pattern on a distant screen would be two patches where the particles hit, and the rest of the screen would have no hits. But the actual double slit behavior doesn't look like that. So that's why people say that light is a wave, although there are other measurements that I'm not going to describe here that prove equally strongly that light is a particle. Einstein got his Nobel Prize for that insight. Okay, now we can start monkeying around with the double slit experiment. What happens if we set up a detector around the two slits to see if the photon goes through one slit or the other? That shouldn't happen with a wave, but it does with a photon. And if you do that, the pattern on the distant screen looks like it's a particle. So this is definitely weird. In the past, people have interpreted this as saying that photons act like waves when you're not looking at them, but particles when you are. In the 1930s, people talked about the influence of human consciousness on quantum mechanics, which has persisted for nearly a century in some communities. Science has long since discarded the special nature of human consciousness in quantum physics, but has certainly started a cottage industry of quantum woo with such books as The Tao of Physics, The Dancing Woolly Masters, and a lot of things said by modern-day television personality Deepak Chopra. None of these reflect current physics thinking. Woo aside, the mind-bending behavior of photons gets weirder still. Let me walk you through this cranial catastrophe. It turns out to be possible to turn down the intensity of a light source so low that only one photon is emitted at a time. What happens when you shoot a series of those photons at a double slit experiment and don't look to see what slit it went through? Will it act like a particle or a wave? Now I need to be honest and say, although this experiment has been done with photons, it was first done using electrons. Electrons, like photons, have both a wave and a particle nature. This means that qualitatively, the electron experiments can stand in for photons. And in 1986, Philippe Grangier, Gerard Roget, and Alain Aspect did an equivalent experiment with photons. I put a URL of their actual paper if you want some light nighttime reading, and by light I mean heavy. And I also added a link to a URL of a paper that details how to do the experiment with university undergraduate laboratory equipment. You know, just in case someone out there wants to check on what I'm saying. So what happened? Well, when the photon is aimed at the two slits, and if light were acting like a wave, you'd expect a very faint interference pattern to appear. Then, with each photon, the interference pattern will get brighter and brighter. But that's not what we see. Instead, we see that the photon is detected as a single spot on the screen. That's definitely the behavior you expect from a particle, so that's pretty weird. We now have two instances where light acts like a particle in the double-slit experiment. If what I said seemed weird, what I'm about to say pegs the bizarrometer. What happens when we send another photon through? Well, just like the first one, it appears in a single spot. But what happens with the third, fourth, hundredth, millionth, and zillionth photon? You see that they start building up a pattern that you should recognize. What you see is the traditional interference pattern seen by Thomas Young way back in the early 1800s. So this is extraordinarily weird. It seems that individual photons travel through both slits, yet they are detected like a particle and also seem to be governed by the mechanics of waves. Light truly has wave and particle properties. Now, the first thing I want to say is that what I've told you here are experimental facts. There is no question that these things happen. These can't be denied. The real question is, what story is the data telling us? That's where things get more complicated. There is the shut up and calculate school of thought, which says that you shouldn't ask what's going on. The theory predicts the result, and that's good enough. Then there is pilot wave theory, which has particle photons surfing waves of probability which guide the photons to their arrival point on the screen. The many worlds interpretation essentially says that all possible outcomes are predicted, and the photon simply follows one of the paths, meaning that there is no tension between the wave and particle nature of light. There are many interpretations of quantum mechanical data. You can look at the Wikipedia to see the smorgasbord of ideas available to you. And there's no lack of ideas that can reasonably be called fringe. I put a URL to the Wikipedia page that lays out the more plausible options. I haven't told you which of the options is right because the jury is still out. Few of the options are ruled out by the data, so we're kind of stuck in the position of saying, I don't know. By the way, fun fact, I went into physics hoping to solve this quantum conundrum, but as I got into it, I saw just how hard it was. If a century of smart people thinking about it hasn't solved the problem, I probably wasn't going to either. So I went to particle physics, which was equally interesting in a field where I could make a difference, and, well, the rest is history. Even though the double-slit experiment is mind-blowing, there's more to the story. In my next episode, I'll tell you about how we can pick which slit the photon went through, then erase that information. What happens in that case? Well, you'll have to watch the next video to find out. Well, that was certainly fun. Thinking about quantum mechanics is always a good way to make your head spin. If you like the video, please like, subscribe, and share on social media. We need more viewers. And what kind of viewers do we want? Well, that's easy. We want viewers who know the great truth, which is that physics is everything.